Section 1 Introduction. We're going to talk about how large language models, or LLMs, are being used in recommendation systems, a topic that's been getting a lot of attention in research lately. Many studies have looked at using LLMs directly as the models that make recommendations. They do this by creating prompts that include the task of making a recommendation, the user's profile, the attributes of the item, and the interactions between the user and the item. These specific prompts are then given to the LLM, which is asked to predict how likely it is that a user will interact with an item. While these studies show that LLMs can be very effective at making recommendations, they mostly focus on using the LLM directly for this purpose. In our study, we're looking at the problem from a different angle. Instead of using LLMs as the models that make recommendations, we're investigating how to use prompting strategies to enhance the input text with LLMs for personalized content recommendations. We're taking advantage of LLMs that have been fine-tuned on large language datasets, with the goal of using them to create high-quality, context-aware input text that will improve recommendations. In particular, we're proposing a method called LLM-Rec prompting, which includes various prompting strategies designed specifically for personalized content recommendations. These strategies include basic prompting, recommendation-driven prompting, engagement-guided prompting, and a combination of recommendation-driven and engagement-guided prompting. By using these strategies, we hope to improve the input text generated by LLMs and make content recommendations more accurate and relevant. We've conducted extensive experiments to evaluate how effective the LLM-Rec framework is, and we've compared it to other basic approaches. Our study offers insights into how different prompting strategies affect the performance of recommendations and highlights the potential of using LLMs for personalized content recommendations. Section Summary. In recent research, the use of large language models, LLMs, in recommender systems has gained attention. While previous studies focused on using LLMs directly for recommendations, this study explores prompting strategies to enhance personalized content recommendation. By leveraging LLMs, the study aims to generate high-quality and context-aware input text for improved recommendations. Different prompting strategies, such as basic prompting, recommendation-driven prompting, and engagement-guided prompting, are proposed to enhance the accuracy and relevance of content recommendations. The study evaluates the effectiveness of the LLM-Rec framework and provides insights into the impact of different prompting strategies on recommendation performance. Section 2 LLM-Rec prompting. We're going to discuss a method called LLM-Rec prompting, which is divided into two main parts: basic prompting and recommendation-driven prompting. In the basic prompting section, we use three different prompts, which we'll call Prompt 1, Prompt 2, and Prompt 3 for simplicity. Prompt 1 asks the language learning model, LLM, to rephrase the original content while keeping the same information and not adding any new details. Prompt 2, on the other hand, asks the LLM to summarize the content using tags, with the goal of creating a shorter overview that still captures the main points. Finally, Prompt 3 instructs the LLM to identify the main characteristics of the original content and provide a response that is more general and less detailed. The specific prompts and the LLM's responses to them can be seen in the upper part of the figure. Moving on to recommendation-driven prompting, this strategy involves adding a recommendation-focused instruction to the basic prompts. We'll refer to these as Rec Prompt 1, Rec Prompt 2, and Rec Prompt 3, which correspond to their counterparts in the basic prompts. The specific prompts and the LLM's responses to them can be seen in the lower part of the figure. Using recommendation-driven prompting has several advantages that make it a great method for creating high-quality content descriptions. 1. Enhanced context. By clearly stating that the content description is meant for recommending content, the models have a better understanding of the task. This extra context helps the models align their responses more closely with the goal of creating content descriptions for recommendations. 2. Guided generation. The specific instruction serves as a guide for the models, directing them to create content descriptions that are more suitable for recommendation scenarios. Mentioning content recommendation likely encourages the LLM to focus on key features and details that are most useful for guiding users to their preferred choices. 3. Improved relevance. The instruction helps the LLM create content descriptions that are tailored to the needs of content recommendation. This alignment with the recommendation task results in more relevant and informative descriptions, as the LLM is encouraged to highlight aspects that are important for users looking for recommendations. Section Summary. In this section, three basic prompting strategies, P1, P2, and P3, are introduced, each instructing the LLM to paraphrase, summarize, or provide a categorical response to the content description. Additionally, recommendation-driven prompting strategies, P1-Rec, P2-Rec, and P3-Rec, are proposed, which enhance context, guide generation, and improve relevance by explicitly mentioning the content recommendation task. These strategies help the LLM generate high-quality content descriptions for recommendation purposes. Section 2.3 Engagement-Guided Prompting. We're introducing a strategy called engagement-guided prompting to improve the way we generate content descriptions for recommendation tasks. This approach uses user behavior, specifically user item engagement, to create prompts that help our language model, LLM, better understand the characteristics of the content that align with user preferences. We denote this variant as engagement prompt. To create an engagement prompt, we combine the description of the target item, which we'll call target description, with the descriptions of a certain number of important neighboring items. We determine the importance of these neighboring items based on user engagement. We'll provide more details about this in the experiment section. The prompt is then formed by merging the information from the target description and the descriptions of the important neighboring items. The prompt might look something like this. Summarize the commonalities among the following descriptions: target description, description of first important neighbor, description of second important neighbor, and so on. There are several reasons why an engagement-guided prompt can help the LLM generate more useful content descriptions for recommendations. 1. Contextual relevance. By including information from both the target item and its important neighboring items, the prompt provides the LLM with a wider context and a more comprehensive understanding of the content. This helps the LLM generate descriptions that are more relevant to the specific item and its related items, making them more useful in recommendation scenarios. 2. User preference alignment. By including descriptions of important neighboring items, which are chosen based on user engagement, the LLM can better align with user preferences. By considering items that users frequently engage with, the generated descriptions are more likely to capture the characteristics and features that appeal to the target users. This makes the descriptions more effective in recommending items that align with user preferences. 3. Enhanced recommendation quality. The engagement-guided prompt uses user engagement data to identify important neighboring items. By including information from these items in the prompt, the LLM can potentially uncover meaningful connections, similarities, or relevant aspects between the target item and its neighbors. This can lead to more accurate, informative, and high-quality content descriptions, thereby improving the overall performance of the recommendation system. Section summary. The engagement-guided prompting strategy, referred to as P-Eng, leverages user behavior to design prompts that guide the language model, LLM, in generating more meaningful content descriptions for recommendation tasks. By incorporating information from both the target item and its important neighbor items, the prompt provides LLM with a broader context and aligns with user preferences, resulting in more relevant and higher quality content descriptions for effective content recommendation. Section 2.4 Recommendation-Driven plus Engagement-Guided Prompting. We're introducing a new type of prompt that combines both recommendation-driven and engagement-guided instructions. We call this the engagement recommendation prompt. Here's how it works. We start with a description of an item. Let's call it D_target. Then we ask, how would I recommend this to others? We also consider that this item shares some appealing features with other descriptions, which we'll refer to as D_1 foot, D_2 feet, and so on, up to D_T. Now, let's talk about our experiment setup. We're exploring the world of content recommendation prompts for large language models, using a well-known recommendation benchmark. Our evaluation setup consists of three main parts: the item module, the user module, and the recommendation module. We keep the user module and the recommendation module the same across all our baseline tests. The only thing that changes is the augmented text, which is created by the language model, or LLM, using different prompts. This means that the augmented text is the only thing that sets the baselines apart. To evaluate the quality of the augmented text in the context of the recommendation task, we've carefully designed and carried out an empirical experiment. This allows us to measure and compare the performance and effectiveness of the different prompts used across the baselines. We're using the MOVIELENS1M dataset as our benchmark. This is a widely recognized dataset often used for testing item recommendation systems. It includes over 1 million ratings from 6,040 movie lens users, covering 3,900 movies. Each user has given at least 20 ratings. We've converted the rating data into implicit feedback, meaning each entry is marked as 0 or 1 to indicate whether the user has rated the corresponding item. The original movie data only includes movie titles and genres. So, we used GPT-3 to generate a content description for each movie. We asked GPT-3 to summarize each movie in one sentence, without including the movie title. The response from GPT-3 is then used as the content description. We set the temperature at 0 to generate more focused and deterministic responses. Section Summary. In this section, the authors propose a recommendation-driven and engagement-guided prompting approach for content recommendation using large language models. They conduct an empirical experiment using the MOVIELENS1M benchmark dataset to compare the performance of different prompts. The dataset consists of ratings provided by users for movies, and the authors use GPT-3 to generate content descriptions for each movie. Section 3.1.2 Item Module. In this section, we'll discuss the item module, which is a part of our evaluation process. Firstly, we focus on the performance of a specific version of GPT-3, known as Text DaVinci 003. This model is a step up from the Instruct GPT models, with several enhancements. We chose this model because it consistently produces high-quality writing, handles complex instructions well, and is proficient in generating longer content. Next, we use Sentence BERT to create textual embeddings from the original content description and the augmented text. The model we use for this is All-Mini LML6 v2. We also use several baselines for comparison. These include basic prompting, represented as P1, P2, P3, recommendation-driven prompting, represented as P1-Rec, P2-Rec, P3-Rec, engagement-guided prompting, represented as PUNG, and a combination of recommendation-driven and engagement-guided prompting, represented as PUNG-Rec. We also have a baseline where no augmented text is added, and the only input is the original content description, represented as CD. The architecture of the module involves combining the augmented text embeddings and the original content description embeddings. We do this by concatenating them and then passing them through a two-layer multi-layer perceptron, MLP. In most baselines, the first MLP layer has an input dimension of 768, except for the baseline where only the original content description, CD, is used as input, which has an input dimension of 384. The output dimension of the first MLP layer, as well as the input-output dimensions of the second MLP layer, are all set to 128. We apply a ReLU activation function and a dropout layer to the first MLP layer. We also measure the importance of engagement-guided prompting. We use the Personalized PageRank (PPR) score as the importance measurement. We first create a user item bipartite graph, represented as G equals V, E, where G is the bipartite graph, V is the set of nodes, and E is the set of edges. There are two types of nodes, users and items. An edge is created between a user node and an item node if the user interacts with the item. We then calculate the PPR score for each item node to determine their relative importance from an individual node's perspective. We identify the top T item nodes with the highest PPR scores that share the same genre as the target item node. This helps us identify important neighboring items based on user engagement. The idea behind this is that if users frequently engage with two items, they likely have similar preferences. By incorporating this information, we can better capture user preferences, which improves our content recommendation performance. For the MOVIELENS1M dataset, we set T equals 3. Section Summary. The item module in our evaluation focuses on assessing the performance of GPT-3, specifically the Text DaVinci 003 variant, which consistently generates high-quality writing and effectively handles complex instructions. We use Sentence BERT to derive textual embeddings from the original content description and augmented text, and combine them using a two-layer MLP architecture. Additionally, we employ Personalized PageRank (PPR) scores as an importance measurement for engagement-guided prompting, identifying essential neighbor items based on user engagement to enhance content recommendation. Section 3.1.3 User Module. In Section 3.1.3, we discuss the user module. We use a special table, known as an embedding table, to transform user IDs into hidden or latent representations. For the MOVIELENS1M dataset, we set the output dimension to 128. In Section 3.1.4, we talk about the recommendation module. We use a simple dot product method in our research. We calculate the dot product of the hidden representations of the user and the item. We then pass this value through a sigmoid function, which transforms the dot product into a final relevance score between the user and the item. In Section 3.1.5, we discuss model training. We use the binary cross-entropy loss to train the model. We consider each user-item interaction as a positive sample. We also randomly select negative samples by pairing users and items that have no recorded interactions. To avoid overfitting and improve training efficiency, we use an early stop mechanism. We also considered using the Bayesian Personalized Ranking (BPR) loss within our framework. However, after testing, we found that the BPR loss did not perform better than the binary cross-entropy loss. Therefore, we decided to use the binary cross-entropy loss as our main loss function. In section 3.1.6, we discuss evaluation protocols. To measure the performance of our recommendations, we use the evaluation method used by Wei and colleagues. We first randomly divide the dataset into training, validation, and testing sets in an 8:1:1 ratio. We create negative training samples using random negative sampling. For the validation and testing sets, we pair each observed user item interaction with 1,000 items that the user has not interacted with before. We ensure that there is no overlap between the negative samples in the training set and the unobserved user item pairs in the validation and testing sets. This ensures the independence of the evaluation data. To evaluate the performance of top K recommendations, we use common metrics such as precision at K, recall at K, and NDCG at K. In our case, we set K equals 10, meaning that we consider the top 10 recommendations. We report the average scores across 5 different splits of the testing sets, providing a thorough evaluation of the recommendation performance. Section summary. The user module in our model converts user IDs into latent representations using an embedding table, with an output dimension of 128. The recommendation module calculates the dot product of the latent embeddings of the user and the item, passes it through a sigmoid function, and transforms it into a relevance score. We train the model using the binary cross-entropy loss, considering each user item interaction as a positive sample and randomly selecting negative samples. We evaluate the recommendation performance using metrics such as precision at K, recall at K, and NDCG at K, with K set to 10, and report average scores across 5 different splits of the testing sets. Section 3.1.7 Parameter Settings. In the section titled Parameter Settings, we start by randomly setting the model parameters, using a Gaussian distribution as our guide. To fine-tune the model, we use the Atom W algorithm, with a weight decay value of 0.0005. We experiment with different learning rates and dropout rates, specifically 0.0001, 0.0005, 0.001 for the learning rate and 0.1, 0.3, 0.5 for the dropout rate. We select the settings that give us the best recall at K results on our validation set, and then use these settings to evaluate our testing set. We check the performance every 5 epochs, and we've set up an early stop mechanism that waits for 5 epochs before stopping. We also set the batch size to 4096. In the Implementation Details section, we explain that we used PyTorch to implement our methods and conduct our experiments. We used the Torch PPR library to help us calculate PPR scores. We ran our experiments on a NVIDIA A100 GPU with 40 GB of memory, using 1 GPU at a time. In the Results section, we discuss the performance of our recommendation system. We found that combining augmented text with the original content description improved the recommendation performance. This suggests that all 3 types of prompting, basic, recommendation-driven, and engagement-guided, provide valuable additional information that helps the recommendation module to model content recommendation more effectively. We also found that recommendation-driven prompting primarily enhances the generation of text input for content recommendation. However, when we compared the performance of 2 prompts that instruct the language model to deduce the characteristics of the original content description, we saw a decrease in performance. This suggests that the reduced recommendation performance may be due to a mismatch between the inferred context and the original context. We also observed that engagement-guided prompting, which incorporates engagement signals into prompts, allows the language model to generate responses that better align with user preferences. Among all the baselines, the combination of the original content description with augmented text generated from both recommendation-driven and engagement-guided prompts achieved the highest performance gains. To further investigate the quality of the combined augmented text, we concatenated the embeddings of the responses from several prompts, along with the original content description. We then conducted the same experiment again, searching for hyperparameters in the same way as before. On the testing set, the precision at 10, recall at 10, and NDCG at 10 scores were 0.3109, 0.2695, and 0.3891, respectively. These results outperformed the model that only uses the original content description by an absolute gain of 1.95%, 2.55%, and 2.65%, respectively. This finding emphasizes the added value of incorporating both recommendation-driven and engagement-guided prompts for augmenting text, to further enhance the recommendation performance over using the original content description alone. Section summary. The model parameters are initialized randomly and optimized using the ADAM-W algorithm with a weight decay value of 0.0005. The learning rate and dropout rate are chosen from a grid of values, and the settings that achieve the highest recall at K on the validation set are used for evaluation on the testing set. The implementation is done using PyTorch, and the experiments are conducted on a NVIDIA A100 GPU. The recommendation performances show that combining augmented text with the original content description improves the recommendation performance, and engagement-guided prompting leads to better alignment with user preferences. The combination of recommendation-driven and engagement-guided prompts achieves the highest performance gains compared to using the original content description alone. Section 5 Discussion. In our research, we've delved into the potential of LLM-Rec prompting as a simple yet powerful tool for enhancing personalized content recommendations using large language models. Our study has led us to several important conclusions. Firstly, we found that blending augmented text with the original content description significantly boosts the performance of our recommendations. This underlines the importance of adding extra context to make our recommendations more accurate and relevant. Secondly, our experiments with recommendation-driven and engagement-guided prompting strategies show that they can effectively guide the large language model to create high-quality input text specifically designed for making recommendations. These strategies use the goals of the recommendation and signals of user engagement to steer the model towards creating more appealing recommendations. Thirdly, when we combine both recommendation-driven and engagement-guided prompting strategies, we see the best overall performance in our recommendations. This indicates that these strategies work well together and can collectively enhance the quality of our recommendations. However, our research has also revealed a potential drawback when using LLM to augment input text in recommendation systems. We've noticed a difference between prompts that only instruct the LLM to alter the content description and those that ask the LLM to infer extra information. In cases where the LLM needs to infer beyond the original context, the recommendation-biased prompting strategy might not deliver the expected benefits. We suspect that the quality and relevance of the inferred context could unpredictably affect the overall performance of the recommendations. This highlights the need for careful thought and evaluation when choosing prompts, especially when asking the LLM to infer information beyond the given context. In addition to its excellent performance in personalized content recommendation, using engagement signals in prompt designs could have wider benefits. The engagement-guided prompting strategy guides the LLM to find commonalities among different items, similar to the concept of neighborhood aggregation in graph neural network (GNN) learning. This suggests that engagement-guided prompts could potentially replace the learning process of GNN, simplifying the overall model structure. Moreover, using the fine-tuned LLM opens up the possibility for zero-shot generation without any additional learning cost. Since the LLM has already been trained to understand linguistic patterns and semantics, it can generate responses or recommendations in new situations without needing further training. This flexibility and scalability could make recommendation systems more efficient and adaptable to new domains or contexts. The combination of engagement-guided prompting and the zero-shot generation potential of the fine-tuned LLM offers exciting opportunities for streamlining model architectures, reducing computational complexity, and broadening the applicability of recommendation systems. Further research in this area could lead to innovative techniques for efficient and effective personalized content recommendation. Section summary. In this study, the effectiveness of LLM-Rec prompting for improving personalized content recommendation through large language models was investigated. The findings show that incorporating augmented text with the original content description significantly enhances recommendation performance, and recommendation-driven and engagement-guided prompting strategies encourage the model to generate high-quality input text tailored for recommendation purposes. Combining both strategies achieves the best overall recommendation performance, highlighting the importance of prompt design. However, there is a potential limitation when using LLM for augmenting input text, particularly when prompts require the model to infer additional information beyond the provided context. The incorporation of engagement signals in prompt designs may have broader benefits, resembling the concept of neighborhood aggregation in graph neural network learning and enabling zero-shot generation without additional training. This presents opportunities for streamlining model architectures and expanding the applicability of recommendation systems. Section 6 Related work. 6 Related work. Besides using language learning models, LLMs, directly for making recommendations, there have been attempts to enhance the input side of personalized recommendations using LLMs. For example, Chen and his team integrated user behavior history, like clicks, purchases, and ratings, into LLMs to create user profiles. These profiles, along with the history of user interactions and potential items, were used to create the final recommendation prompt. LLMs were then used to estimate the probability of a user interacting with an item based on this prompt. However, our research takes a different path, focusing specifically on enhancing the input for items. Through the use of prompting strategies, we aim to create enhanced input text that more accurately reflects the features and subtleties of items, leading to better personalized content recommendations. Xie and his team proposed a method that uses the reasoning abilities of LLMs about user preferences and the factual knowledge of LLMs about items to enhance input features. Their method assumes that LLMs have factual knowledge about the items to be recommended. However, our research differs in its underlying assumptions and prompting strategies. We don't assume that LLMs inherently have factual knowledge about the items to be recommended. Instead, we focus on enhancing the input text solely through item descriptions, thereby broadening the range of items to include those with only textual descriptions. Moreover, based on this assumption, we have developed various prompting strategies specifically designed for personalized recommendations. These strategies consider the unique nature of the input text enhancement process and are designed to maximize the performance of the recommendations. Section summary. Previous work has explored using language models, LLMs, for personalized recommendations by incorporating user history behaviors and generating user profiles. However, our study focuses on augmenting the input text for items, using prompting strategies to capture item characteristics and improve personalized content recommendations. Unlike other studies, we do not assume that LLMs possess factual knowledge about the items, but instead focus on expanding the scope of items with textual descriptions and designing tailored prompting strategies for optimal recommendation performance.